Well, we'd like to see how to find the E field if we know the potential. And to start with, we have to review a little bit just so we remember what these quantities mean. We get the electric potential by starting with the potential energy. And if you remember, we derived the difference in potential energy between 2 points. For example, pushing this charge Q0 from A to B, if we're doing work and it's positive, then we're increasing the potential energy as we go from A to B. The force on the charge is of course related to E, and so we end up with an E dependence for this because E is what's pushing on the Q0. To find the potential, we take this equation here and we divide by Q0. And so I've done that as I did before, and so if we take the above equation, we end up getting right here the potential at B, right here the potential at A, and over here we will lose our Q0 because there's a Q0 in this force. Remember, force on Q is Q0 times E. When we divide by Q0, we drop that, and so we have a function which is only the function of the E field to give us the difference in potential. Don't forget this minus sign. The purpose of that minus sign, for example, is if you're pushing the charge with you're having to do work to get from A to B, this minus sign will assure that you're getting the increase in potential as you should. So here's the equation again. It's helpful to use the vectors that point at the 2 points. So this vector points at the position B, and this vector here points at the position A. We quite frequently take this vector to be pointing at a reference point. Sometimes we set that equal to 0 just to get rid of it. Frequently we are using infinity as our reference point. Going back to this equation here with just the substitutions, then the change in potential at the position R versus R0 is equal to this quantity here, where you see we're integrating from the point that's represented by R0 to the point that is represented by R. Again, sometimes we just set this equal to 0, so that gives us the potential function all by itself. I want to go back to the gradient because that's what we're going to end up looking at. But let's start with one dimension first. So if you have a function which is a derivative of a function and you put that function into an integral, then obviously if you integrate, you're going to end up getting something like the function itself. It's the antiderivative, so to speak, when you take the integral. If we go from the point A to B, then you remember the fundamental theorem of calculus tells you that this integral is equal to the value of the function at B minus the value of the function of A. Remember, f is the one that you're taking the derivative of to get the argument for the integral right here. Well, in 3 dimensions, instead of taking just a simple derivative, we end up needing the gradient. If I substitute R and R0 in for A and B like I just mentioned, we'll start with a scalar function, which is a function of the position, and I will give without proof that if we write what looks like the fundamental theorem of calculus using the gradient, this is an analog to this equation right here. So if we take the gradient of the function and we're integrating over a dummy variable, I put primes on them, but you could have called it something else, then we're going to end up with the scalar function evaluated at little r vector minus the scalar function evaluated at r0. And you can think of this as the reference point. This equation here is called the fundamental theorem of gradients, and I think for our purposes what you can think of is that it's just an analog between the fundamental theorem of calculus and going to 3 dimensions. If we compare the function that we have here where VR minus VR0 is equal to this integral here, if we let v equal t, this difference here is this side of the equation here. Over here we have minus something dot dl. Well, that something we can equate to the gradient of t. And so doing that, we can write that the electric field is the gradient of a function, and in order to take care of this minus sign, we have to put a minus sign here. What is going on? If the potential is changing in such a way that we have to do more work in going from R0 to R, then that minus sign will be required in order to have the E field pointing in the right direction. If we have this quantity right here, if we're given a V, we can find E. And by the way, this was a dummy variable. I didn't evaluate the whole thing. It'd be better if you just cross these out, and so just have the position vector r and the position vector r. Remember, we're taking the gradient with respect to the r and not the r prime vectors. So in general, the scalar function v of r is easier to calculate. And so once you know it, you can find E by just simply taking the gradient. That's the big advantage of this equation and using the potential. Well, let's go to a very simple case, and that is the E field due to parallel charge sheets. If these are infinitely long or just very, very large, we can have a minus charge sheet and a plus one separated by some D. And in the space between, you remember we got an E field, and that E field was uniform throughout that whole space. We were able to get this with Gauss's law, where we used pillboxes. So for example, a pillbox right here, initially we found that the E field outside was 0, and so we were able to find the E field inside, either here or over here. They're both the same. I've represented this as a field going from this side to this side, and that's what you expect, because this is a plus charge and this is a minus charge, and so that's the direction that the field would have to be. So we're going to assume a potential and show that it actually is very reasonable. It's a constant v0 times the position vector x, and x goes from 0 to d. In this diagram here, x goes in this direction here. This would be 0, and this would be x equal d. The problem that we're talking about could be replaced by taking conducting plates in the same position as those charge sheets and putting a battery in between them. If we want to get this minus and this plus, you make this the minus terminal of the battery and this the plus terminal. By the way, the function of the battery is to pump charge. When the battery is in this polarity, it pumps negative charge around here and then puts it onto this plate. If you remove minus charge, you end up with a plus charge. So that's what the battery does. In terms of keeping the potential so that it fits this equation, we're going to ground this side, because what that does is give us 0 volts on this plate. I want to make sure you understand that you can have this at 0 potential, you can ground it, which means you find a big large object like the building conducting pipes and everything. Those would be at 0 volts. So when you hook these together, you get 0 volts. But nevertheless, you can have charge on this sheet here induced by this separation of charge that I told you about. Think of it this way. If you have this ground and you put a positive charge sheet here, what's going to happen is that that's going to pull negative charge up here so that this remains at 0 volts. Because this is a positive charge sheet, it would tend to produce a potential here. But if you put negative charge here, you'll get 0 volts. We're given that this is the potential. We find the E field by just taking minus the gradient. Since it's a function of x only, we just differentiate with respect to x. The direction of the field will be in the x hat direction, and it'll be minus the x hat direction because of this minus sign right here. You can see that the x is taken away by taking the derivative, and we only get v0, and so the final answer is that this is just minus v0 x hat. So it's a field that's constant in points in the minus x direction, which is exactly what we drew here. It's a constant, so therefore it's consistent with what we said in terms of charge sheets. Get a constant E field in here. If you knew the magnitude of V0, then you could get the magnitude of E. Well, let's go back to the battery. If we go to the position x equal d, so we go from 0 over to this plate here, if you look at our potential, this one right here, you put in x equal d, you get V0 d. Now the battery is a source of potential difference. We said this was 0. This voltage here is in fact the voltage of the battery. So we can set those two equal. Constant, which we just simply chose as a constant in front of the x, will be equal to V battery divided by D. If you now put in your E sub x, the E field, and replace V0 with this quantity here, then you have minus V battery over D times the x hat. This V0 is like the total potential across a gap divided by the distance across. It's a very useful way of looking at uniform fields between plates. The net result, if you have a constant potential, constant D, and the plates are large enough, you will get a potential that depends on the position linearly between one plate and the other. If you take the gradient, you get the E field that you want, which is namely a constant field given by minus V battery over D. Well, let's do another problem. We're going to actually use the results of a derivation that I'm going to give you later. And the results I'm going to give you is the potential. You're given the potential either inside of a sphere or outside of the sphere. The problem is to find E. So obviously, if we have the potentials, we can just take the gradients. The problem is defined in terms of a parameter z rather than little r, and that's simply because the way I derived it. And we'll convert to r when we finished. Okay, so here's a point inside, and here's a point outside. They're going to be different in some respects in terms of what happens. So let's take a look at that. Well, here's what we derive, or will derive. This is the potential at the position z if we're outside of the sphere. If we do the problem, what we find is that it's equal to this quantity here, so there's a prefactor here that has little k, sigma, and the radius of the sphere squared. And then it has 2 over z, which we can then use k as 1 over 4 pi epsilon naught and simplify this to this equation here. So it's sigma r squared over epsilon 0 over z. So it has a potential that falls off 1 over z as you leave the outside surface and head out to infinity. Inside, when we do the problem, we find that the potential replaces the z with capital R. And so when you simplify this, you can see that if you have r squared over r, you just get an r. And so this is the result inside. And it's clear that that's a constant. So I've rewritten the equations that we're going to derive. Let's find the E fields. We're going to start by looking outside, so we're going to use this one up here. We're going to differentiate it, or take the gradient, and we'll only need the z component because there's only one variable in the function. So we'll have minus partial with respect to z of this function. The gradient will give us, of course, the z hat. Differentiating 1 over z with the minus sign gives us a plus 1 over z squared. And so we end up then with the E field outside that looks like this. Let's put it in terms of r just so you'll have this in your notes. If we switch to r, then this becomes E of r hat. And so we put in our r's and we end up then with this equation here. And so one reason for doing it is because you can see right away that that's the E field due to a point charge. That's consistent with Gauss's law because remember you took a Gaussian surface on the outside at the distance r, and you found through symmetry arguments you could find that E field, and it was equal to all the charge on the sphere concentrated at the origin. The results of using the derived potential gives us the same result, so that gives us some confidence that we have the right answer up here. Now we go inside, so we use this expression here. And so we do the same thing. We take the derivative with respect to z with the minus sign. We get the same partial derivative. What do we have? Well, this doesn't depend on z, so we end up with 0. For all points inside then, the E field is 0. Just repeating that, let's do our transformation to r. We end up with E of r, this is a scalar, times r hat, only depends on r, and that's equal to 0. If you have this condition where you have uniform charge density on the surface, the spherical symmetry would also lead to the same result if you have no Q inside a Gaussian surface. So you take a spherical surface out here at R, so you're inside. Using the symmetry arguments, you can show that the E field is radial so that when you do the Gaussian integral, it separates out. There's no charge inside, so you end up with 0, and so the E field is equal to 0.